Hey everyone, welcome back to my channel. In this video, I'm going to build a simple image tagger on GCP. What our ML image tagger would do is it will tag an image with a few keywords based on the objects that are present in the image. Let me explain to you what we are building in a little bit more detail. So here in the diagram you can see we start with our user who uploads an image to our image service. Our image service has three other services. We have a GCS service, we have an object detection service, we have a DataStore service that the image service will be using the functionality from. Once the user uploads the image, it will write that image to GCS or Google Cloud Storage. This is denoted by the series of red arrows in the diagram. Once the image is uploaded, then we will hit the Cloud Vision API with the image and get a set of tags based on the objects that are present in the image. Cloud Vision API provides an object detection API which we will be using to get the objects that are present in the image. Once we obtain the tags, we will write this data to GCP DataStore. GCP DataStore is a NoSQL document store, which provides fast and scalable way to read and write data. When you are writing to DataStore, you have to write in entities. So you can see the entity we have defined here. Our entity has an image ID, an image URI, and a bunch of object tags. The object tags is a list of strings. I have noted a few implementation details here. We will be using Java and we will be using the Spring framework. This whole service will be hosted in App Engine. App Engine provides an easy way to deploy a service. It provides a variety of functionalities such as load balancing, traffic splitting, and etc. Another thing I like to do is understand the pricing for each of these services we are using. So let's have a look at this pricing. First, let's look at the GCS pricing, Google Cloud Storage pricings. So let's type GCP, GCS pricing. If you scroll down a little bit below, you will see that we're getting charged per GB per month. Since we're doing this as a toy example, we shouldn't be worried too much about it. Per gigabyte, we will be charged about 2 cents, even in multi-region settings. Next, let's look at the Cloud Vision API. So if you scroll down here, you can see in object localization, the first 1,000 units per month is free. Then from unit 1001 up to 5 million, you will get charged $2.25 per 1,000 units. So again, it's pretty reasonable for our toy project. Next, let us look at the DataStore pricing. So here you can again see that we are getting charged per entity reads and entity writes. So you can see GCP offers generous limits per day. So here the first 50,000 entity reads per day is free and the first 20,000 entity writes is free. This should give us really good wiggle room to go and play around with these services without incurring hefty charges on GCP. So going back to the design, as an MLE, I'm mostly familiar with Python, but I actually decided to go with Java and implement these services in Java with a little bit of help from ChatGPT. Why is it a good idea to choose Java over Python to implement the backend? There's many different reasons. For example, Java has really stood the test of time for enterprise application development. It has strong support for multithreading and concurrency, as opposed to Python, which has the global interpreter locking mechanism, which leads to inefficiencies when dealing with concurrencies. Java has better error handling because you need to either throw the errors or handle them when dealing with errors in Java. Java is statically typed, making the interfaces and the responsibilities of various methods super clear. As a disclaimer, I'm not a backender or an expert in Java. This is mostly from my own learnings, working with the Java backend for several years, deploying and productionizing models. So if you see something that could be done better, leave a comment which will help others as well as myself. I'm also grateful to the ML Developer Program team who supported this effort by providing GCP credits. Okay, now let's get into the tutorial. The first thing I will do is I will go into my GCP and then I will create a new project. So you can see I've already been working on an ML image tagger project in order to make sure things are working before I go on with the tutorial. But to show it end to end, I will actually start a new project and do it all over again. So the first thing we're going to do is create a new project. So we can go here. Let's do ML image tagger 2. We don't have an organization, and I'm just going to create this project. It'll take a few minutes and then you'll have your project. Okay, so the project is created. So let's go ahead and select our project. Now you can see we're in the ML tagger 2 project. First thing, we have to enable a few different services. So GCS, you don't have to enable it. It's enabled by default. You would have to go to the cloud. Let's enable the Vision API first. So let's click enable. And then let's enable the DataStore. And simply create a database and let's go to, so here let's select the DataStore mode. So we have to select a location. I'm going to implement all my services, or I'm going to have all my resources in United States to make sure that there are no significant latencies for the communication between different services or resources in GCP. Okay, now we have our database. So if you go into all databases, you should see a default database, which is in NAM5, which stands for several regions in the United States. And then finally, we need to enable our app engine. So let's go ahead and click create an application. You're going to select US Central. And the next thing we want to do is create a different service account. The service accounts are important to make sure the GCP resources such as App Engine has all the access it needs to perform the task fully. For example, it needs access to the GCS, it needs access to DataStore, it needs access to Cloud Vision API, and so on. So there's two ways you could do this. One is to use the App Engine default service account. However, it's always recommended to create a service account with least amount of privileges to improve security. So in order to do that, let's actually go ahead and create a new service account. So let's name this ML image tagger. that and continue. And here we have to give it the correct roles. So I'm going to choose 4 different roles. I'm going to give it App Engine Admin. I'm going to give it Storage User. Give Storage Viewer. I'm going to give it DataStore User. Finally, there's a very important role that we need to provide to our app and our service account. That is the token creator, the service account token creator role. This is quite important because one thing we're going to do is when we are running this app locally to test, we're going to impersonate this service account with our user so that the permission we have exactly matches the permission this service account has. So in order to do that, this service account needs the service account token creator permission. I actually decided to go back and do a second take on this part about permission because there are quite a few callouts I need to make and one mistake to correct. Firstly, the App Engine admin role might be too excessive for this particular task. So you might be able to play around with and choose either editor or user type of role rather than an admin role. I kind of did it lazily because I didn't want to spend too much time figuring out the least permission. But if you're building a production system, I would strongly recommend spending some time understanding what is the least privileged role that you can provide to this particular service account. You don't need the service account token creator role for this service account. A service account already knows how to create access tokens. I will explain what I mean in more detail when we are actually running this application in our local environment. So keep an eye for that. Okay. Now we have our ML image tagger service account set up. So what we are going to do is we're going to go back, refresh our list, and select the ML image tagger service. Okay, great. So now we have our application environment set up. The next thing I'm going to do is that I'm going to create a GCS storage bucket to store all the images. So I'm going to go into cloud storage. And here you can actually see we have 2 buckets with the domain appspot.com. These are buckets used by our App Engine. One thing to keep in mind is not to delete these 2 buckets because it will cause issues and it will not let you deploy the apps into App Engine. So do not delete these buckets. So I'm going to create a new bucket. I'm going to call this image server deep learning hero. You can use any name you want, doesn't matter. Okay, it says it's already taken, so I'm gonna do a different name. Let's say ML image tagger 2. I'll simply do one region because I'm not really fussed about deploying it to multi-regions or anything, so I'm just going to use US Central and then use a single region. The type of storage we're going to use is standard. We will have uniform access to all the objects in the bucket, and then we will not enable any data versioning. But always remember that data versioning is really important if you're running a production system. In this case, since I'm implementing a toy example, I wouldn't be worried about data versioning. If you don't enable data versioning, you won't be able to recover any deleted items. So it's super important that you do use the object versioning when you're doing a production system. So I'm going to enforce public access prevention for this bucket because I don't need public access. So now we have our bucket created. So in order to set up our Java code, we'll be using the Spring framework. Spring framework is quite good for Java applications because it provides a lot of functionality out of the box, such as authentication, web app development, dependency injection, and so on. So the Spring framework is also heavily used for enterprise applications. So we will be using that to get the advantages that are provided by the Spring framework. To get a Spring project quickly up and running, you have this website that you could go in and create a Spring project. So in the Spring project generation page, we'll select Maven, the language will be Java, we'll select version 3.1.6, and for the group we'll do Deep Learning Hero, and then the artifact, let's say image server, and let's remove the server from the name. So we have the artifact name and the group set up, and we have our package name, and then we're going to add several dependencies. The first thing we're going to add is Spring Web, which allows us to build RESTful applications using Spring MVC framework. It uses Apache Tomcat as the default embedded container. And then we will also add GCS, GCP storage. And then we will generate. So once it's generated, let's go in. So we have our image server and we have our project files here. So what I'll do is I'll simply copy this into my coding environment or my workspace. Let's simply paste it. Let's create a new folder, say image tagger, and then let's simply paste that here. Okay, and then we will open this using IntelliJ. So I'm using IntelliJ as my IDE. So let's open. So this is a project I've done to test out to make sure everything works. So I'll be copying and pasting things from this particular working project and building up the project we just created. So let's just simply open our project. Should be this one. So trust the project. Let's create a new window. And now we have our project here. The first thing we will do is we will add several dependencies to our POM.XML. So we already have Spring Boot started web, we have Spring Cloud GCP started storage, we have Spring Boot started test. We'll be adding these three packages. So first we're adding Google Cloud Vision. We'll be adding these three dependencies: Google Cloud Vision, we have Google Cloud DataStore, and we have Commons Imaging, which is used for some image manipulation work in the repository. So the next thing we want to create is this resources subdirectory. So I'm going to copy some files from my previous working project and paste it here. So what I'm going to do is I'm simply going to paste it here. So we have this resources subdirectory and we have our application.properties. So application.properties will contain all the properties that are important for your project. So some of this will be coming from certain dependencies, and there could also be custom properties that you want to inject into your code. We have two important properties here. So we have a GCS bucket name and we have Spring Cloud GCP project ID. So this will be set to image tagger 2 because I used ML image tagger to test out my work. So I'm going to set this to ML image tagger 2, which is our new project. And then I'm going to, and I've already set up a GCS bucket name, which is different from this, which is called ML image tagger 2. So I'm simply going to copy that and paste it here. And now we have our application.properties file set up. And then the next thing we have to do is set up our Java code in here. So again, I'm pretty much going to copy and paste it from my previous project, but I will walk you through what I'm doing in these classes. So as I explained in the system design diagram, you have three different services: DataStore service, we have the GCS service, and we have our object detection service. And then finally, to glue all of that together, we have the image server application. So this uses the Spring Web Framework. If you're interested in learning more about Spring Web Framework, I would recommend checking out the Spring Framework official documentation. But as you can see, it makes it really easy to define endpoints in a Java application. So we have three different endpoints. We have a status endpoint, which always returns a service is running. And then we have an upload image endpoint. Then we have a get image tags endpoint. Now let's actually understand what the code does. So let's first maybe go through different services we have here. Let's first look at the GCS service. The GCS service simply takes a bucket name and initializes a default instance of our storage options and then gets the service. It has one function, which is write to bucket. Given a stream of image bytes and a file name, it writes that file into the bucket. You can already see here how we are injecting our gcs.bucket.name into this bucket name through Spring. Once we write to the bucket, we simply return the URI for that particular file as the response, as the return value of our function. Then we have our object detection service. Again, it initializes a client which will communicate with the Cloud Vision API. This service again has detect objects, which accepts a stream of bytes called image bytes. It creates an image object from the Cloud Vision API. Then it says, I'm interested in the object localization. And then it creates a annotate image request. And finally, it retrieves the annotations generated for that image. Once the annotations are generated, we have the extract object names function. This simply goes through all the annotated image responses in our returned object and then get only the object names. This annotation contains other information like confidence, the bounding boxes. We're not really interested in those information yet in this particular project, so I'm going to discard them and only get the object names from the response. So that's what this one is doing. And finally, we have our DataStore service. This one instantiates a client for our DataStore, and then it has one function, persist image tags, given an image ID, image URI, and the object tags of that image. It creates a key called of kind image. So this key will be used to index the data in the database. And then we have the tag values. And finally we create an entity which contains all this information like the object tags, the URI, and simply build that entity. And finally we put that entity in our data store. And finally, all of these are combined together in this particular application. So you can see in the upload image function, we're generating a UUID for each image, which will serve as the ID for that image. We get the stream of bytes from the uploaded image. We generate a file name, and then we write that file into the GCS bucket. And finally, we call our object detection service with the image bytes to get the object tags and use the DataStore service to persist these image tags for that particular image and other metadata information we're interested in. So you can see here we're using the completable features library in order to do this async, because our user is not interested in how much time it takes to go and save this data. So all of this will happen asynchronously, and as soon as the data is written to GCS service, we will return a response with the UUID, and this will happen in the background. And finally, we provide an endpoint where you could just query the data store to get the image tags for a particular UUID. I will provide all of this code in my GitHub repo, and I will have a link to the repository in the description of this video. Okay, now we understand our code. Let's try to build this project. So what I'm going to do is I actually need to open just this folder because I don't think this is yet recognized as a Maven project. So what I'm going to do is I'm just going to click open and then open this particular folder. So once I do that, I can already see the M appearing here, and then I should be able to see the Maven, and then I will do a reload of the project. It might take a little bit of time, so it's downloading the Maven plugins. Okay, looks like we are set up. So the next thing we need to do is we need to set our authentication mechanisms properly. For that, we have to use the command line, and let's go into our folder first. Okay, if you remember, I said that we need a way to impersonate our service account when running this application. So Gcloud, which is the command line interface for Google Cloud, provides a convenient way to do this. You can learn more about how to impersonate a service account in GCP documentation, but I will show you the commands that I'll be running in order to impersonate this service account. So what we have here is, so let's go and have a look at our service account. So we'll simply add that. So what it is saying is whenever you are using client libraries, log in with this particular impersonation. So it says impersonate the service account, which is the service account we created. So let's try running this. Okay, now it's asking me to authenticate. Let's try to authenticate. Okay, so now I'm authenticated. And it says the credentials are saved here, and this will be used by our application in order to make a successful login and then use the GCP resources. Again, I will provide these commands in my repository as well as in the description as much as possible. Okay, now that we have our authentication working, we should be able to go ahead and make a request. So what I'll do is I'll simply run this. Okay. So we have our project set as the ML image tagger and everything is looking good. So I have a bunch of images that I'm using that I use to test our server. So I'm just simply going to copy those into this new folder. So here we'll create this images folder. I'm going to copy that, and I have a bunch of images. So you can see, say, PNG version of a landscape. We have cat in sunglasses, a dog, and a scene from a restaurant. We have a Lightning McQueen, and so a bunch of different images. So I'm going to try to upload one of these images and see what sort of object tags I am going to get for this data. So I already have a command written on what I have to do in order to upload this and hit the API endpoint, and we should be able to run this end-to-end, right? Because we've already impersonated our service account, so we should be able to run this end-to-end. So one thing I haven't shown you is now if we go into our local host 8080 and then do status, we should see services running. So yes, we do see our services running. Now let's paste this. So basically what it's doing is we're first encoding this image into a base64 string, and then we are passing that into the upload image endpoint. And within the upload image endpoint, it can decode this base64 encoding and then convert it to a byte stream and pass it on to other services that uses that byte stream. So let's see what happens. Okay, we got an error. Let's see what was the error. Okay, it says required request body is missing. I might have the wrong path for the image. Oh yes, so it's not cat anymore, I think. It's 2.jpg. So let's try changing our name. And I have a S missing here as well. Okay, let's see now. It still says an internal error. Let's check what happened. Okay, now we have an error. Okay, so we have a permission access. So what I'm suspecting that happened here is my user, the actual user, might not have access to, oh, I know the problem. So I might not be logged into the correct project. So let's do gcloud config set project ML image tagger 2. Okay, now let's add the policy binding. That gives, I think that was successful. So then what I'll do is I'll simply impersonate this service account and see what happens. So I went back and decided to edit the video here. It sounds like I'm rambling a little bit without knowing what actually is going on. So I decided to consult the GCP documentation and understand what exactly these two commands are doing. So here's my interpretation. First, I have myself, who is the principal, and then I have the service account. Service accounts are a bit different to principals or user accounts. Service accounts can act as a resource or it can act as an account. For example, when the service account is carrying out the workload required for the use case, it is acting as an account. But you can also grant certain roles on the service account. One important thing to keep in mind is that when service accounts are carrying out the workload, they're using short-lived credentials to access these APIs. What this particular command does is that it gives the principal, that is myself, the role IAM service account token creator on the service account. So in this case, the service account is treated as a resource. In other words, it is letting me create a short-lived credential to access the use case on behalf of the service account. This is known as service account impersonation. If you're not the owner or if you're not a privileged user in your project, you will need a privileged users to grant this access to your account. In my case, I'm the owner of my project, so I don't really need this. The next workflow we are going to look at is when we are developing our application and we are testing our application in our local environment. We need a way to access our use case or GCP resources from our local environment. In order to do this, we would like to use the service account because it already has all the permission required to carry out the use case. So what this command does is it provides the client library. It provides the credentials required for the client libraries to perform the impersonation of the service account. So once you run this command, your client library can perform this particular impersonation, obtain the credentials, and access the APIs and GCP resources. So the two commands we are running, gcloud IAM service accounts add IAM policy binding, allows you to act as the service account. And then gcloud auth application logging impersonate service account generates the credentials required to access the service account. Okay, now let's restart our app just in case and see if we can get the permission working end to end. Okay, our service has started. Now let's try running this. Okay, now our service actually worked fine. So you can see we've got an image ID for a particular file, and let's check the first check the GCS to see if that file actually exists, and then let's check the DataStore to see if we've received successful image tags. So you can see our UUID starts with 3EE. So let's go into our folder and click refresh. So you can see the particular image is there. And then we can also go into the data store and let's check if our data point is there. So yes, so you can see the 3EE has got tagged with sunglasses and cat, which is exactly what's in the image, and you also have the URI for the image. So you can see the full details here, and yeah, so it all works end to end. Now that we have made sure that it all works end to end, we have to deploy this into the app engine. Deploying it into the app engine is pretty straightforward. All that you have to do is create this app.yaml file. Again, I already have that created, so I'm just going to copy and paste it here. Do a paste, and I'll walk you through. So it says runtime is Java 17, instance class F2. So this is like a fairly low-end machine, so you're not going to incur too much costs. And then we're going to have some automatic scaling, where min instances is 1, the max instances is 3, and the time it will scale up is when the target CPU utilization hits 0.8 or 80% in the current instances. So whenever it reaches 80% CPU utilization, it will add more units or more instances into our app. And once you have this app.yaml, all you have to do is simply we'll have to go into our image service and then do gcloud app deploy. So it asks if I would like to continue. Yes, I would like to. And you can see here we've already got a target URL. This is the URL we'll be hitting once our app is deployed. Okay, now we can see that our app has been deployed, and we should be able to hit this URL and serve requests. Okay, let's go into our app engine and see if we have our app there. We have version 1, and in the dashboard you don't have much data, but for example here, if you go in, you should be able to see the number of instances it is serving, and in the dashboard you will see the latencies and so on. So let's actually make a bunch of requests and see what happens. In order to do that, I have this query.py file. So what I'm going to do is I'm going to open this window. We'll open this window in a new window. And here I have this query.py file. So I'm going to replace this URL with our new URL. Simply going to copy and paste it here. So what it does is it first has two functions: to upload the images in a given directory, and then it has a function to query images based on the UUID. So what it'll do is it'll first upload all the files, it'll sleep for 10 seconds, it'll do a round of warm-up requests, which means we'll just query the images for all the UUIDs once, and then we are going to create a pool of pool of 5 because we have 5 different images here. 5 different images here. So we're going to create a pool of 5, and then for 10 iterations we're going to parallelly query this particular service. And finally, in the final round of results, we will print the actual results and see what sort of different object tags we got. So all I'm going to do is I'm going to go here, comma, might use the Anaconda environment. So I'll just go here and then simply do Python query.py. Okay, think I've copied the wrong URL. So let's go and fix that. Yes, in the haste, I've just copied the service account here. So let's save that and then go back and try to query this. So it looks like it's working fine. Let's see. So it's probably uploaded all the images. Okay, so it's uploaded. It finished a warming up, and now it's querying the data in parallel multiple times. The reason we are doing this is because we want to test how much requests or how much throughput this can stand, and whether it serves our requests with a reasonable latency. So you can see here all the tags are quite reasonable except for one. So the cats and sunglasses is there. It's this image, that's fine. And then we have a, maybe shrink this, and then we have the bicycle wheel and the person dog, which is this image. We have the tableware person food, which is this image. Then we have the wheel tire toy, which is this image. However, you can see that this one is quite wrong. So it thinks it's an animal, but it's actually a landscape. So this is where the confidence might matter a bit more. So when you're actually taking the tags, maybe look at the confidence and record the ones that you have higher confidence for only. But overall, it seems like it's working well. Let's go into our dashboard and have a look at some of the data. So let's check the latencies. Okay, now we have some latency information here. So it looks like the 95th percentile has 165 milliseconds. It's not the best, but at the same time, I'm in Sydney, Australia, and this whole service is in the US, so there's obviously going to be some latency because of the distance between the two, because I'm not using any caching or multi-region replication or anything like that. So I think 160 milliseconds is quite reasonable. But I think we've learned what we need to learn. That is create this automatic ML image tagging service, which will upload an image to GCS bucket and then call the Vision API to get the object tags, and then finally store that into a data store. And then anyone who's interested about these objects can get their object tags from the data store. This has various use cases such as search. For example, you can't expect the users to always enter correct metadata incomplete into the system when they're uploading photos. So in that case, you could use something like that to automatically tag and improve the metadata of those images. Secondly, users might enter irrelevant keywords when they're uploading the images. The ML models will be more accurate and more clean and more sanitized, so you could make the distinction between the provenance of different keywords and use them differently in the downstream use cases. And finally, there's quite a bit of improvements you can make here. For example, you see that I created most of these resources by hand using my own user account, whereas you can use something like Terraform to manage your infrastructure, spin up your infrastructure, take them down quite easily programmatically. Next, you could resize the images before you send that to the Vision API. For example, you don't need to have like a 1024 by 1024 image in order to detect the objects. You might be able to achieve that using a smaller size like 224 by 224 or 512 by 512 or 384 by 384. So test out and find the optimal size and then use that to avoid the amount of communication or the bandwidth required to send the image data. You could use data replication and caching in order to improve the performance, in order to improve the latencies. Again, as I said, I will try to share most of these commands I ran and the code in the GitHub repository and link you the resources. That brings us to the end of this video. Thank you so much for watching. I will try to create more system design tutorials like this over the coming months. If you'd like to see more videos around machine learning and sort of using cloud services to implement various systems, please subscribe to my channel, Deep Learning Hero. I will see you soon with another video.